video will be like most of the others. I'm going to, throughout the lecture, give out a series of attendance words, or sometimes it'll be a phrase, sometimes it'll be a question. Either way, when I give one of those attendance words or phrases or questions, whichever it may be, you need to write it down. And you need to take a screenshot when I say it. For example, right now, the first word for attendance is Snoopy, like the cartoon dog Snoopy. So you should write that down. You should take a screenshot. And then at the end of the video, once you've heard all the attendance words and you've taken all the screenshots, then you should email that to me. In this particular screenshot, I should see an empty room with the screen off and the door open. But yeah, so business as usual. The last word for attendance is going to be me asking you to ask me a question. So as you're going throughout this, as you're listening to the lecture, keep that in mind, that the last word for attendance is going to be you asking me a question about the information presented in this lecture. So that's it. It is 7:30 right now, so we still have about 30 minutes. You can scan ahead, fast forward in this video about 30 minutes, and that's when the lecture will start. Morning. Morning. You have anything fun planned for the weekend? No, me neither. Actually, I take that back. Loose plans. They're playing the original Ghostbusters at the movie theater in St. Albans. I've never been in that movie theater. I think that's the first movie I saw in the theaters, which goes to show how old I was. I was a little kid. But we're going to see that. The kids aren't nearly as excited as I am. It's old people stuff. But it's what it is. Morning. Good morning. Who you playing this weekend?
Concord.
Where are you playing here or
Not there.
there? How far away is that?
I honestly don't know. I think it's like 2-3 hours from see.
It's not bad. It's no Pensacola.
No, that's next.
You guys looking forward to that one? Or do you think you'll be able to enjoy it at all, or is it gonna be like, all right, fly there?
I mean, I think they're having a beach trip.
Oh, cool.
I ain't going that one.
Oh, you're not?
I ain't traveling.
I forget that they have different, like travelers versus not travelers.
Oh, freshman. Registered freshman.
Makes sense, I guess. What about the band? Does the band get to go? Yeah. Just to that, or do they go to any of the away games? Guess we just don't have the money for that, huh?
I would assume that.
Because I've seen other, when you watch it on TV, the bigger universities, you see that they travel with the bands.
Yeah.
I used to have friends in the Florida State band, and they travel.
My high school and community used to travel with us too.
Yeah, we used to too in high school. Well, not the first high school I went to, because we only played home games. We traveled for like competitions. But yeah, the second high school I went to, we traveled for football. And that's when I stopped playing football.
My band's not that big anymore.
That might be it. Well, no, now that I think about it. My first band had like 80 people in it, which is, I think, pretty small.
This band might have like 20 people now.
Wow, that is tiny.
Like that.
Yeah, the one we traveled with was a lot bigger. It was like over 100, which I thought was weird. So it had this huge band. It took at least 2 buses to get the band. And there was the ones that traveled. And then back when I was in the smaller band, we never traveled. But like I said, that's when I played football, so it worked out. It was hard to do football and the halftime show. Didn't have to do that in Georgia, on hand for it. It's gonna be hard. Morning. Good morning. All right, we've got 5 minutes, might as well get started. Make sure we're still recording. We are. So Brumfeld is not here yet. Champion, not here yet. Gross, not here yet. Gunther is here. Wow. Usually Randall Hill is our first one here. Now we've got the other Mr. Hill is our first one. Well, the first Hill here. Jackson, not here yet. Keys is here. First one here. Give you a little extra points for that. Perez is not here yet. Sigmund is here. Slaughter is here. Smith is not here yet. Stover's not here yet. Tompkins is not here yet. Vanessa is not here yet. Watson is not here yet. Young is not here yet. Zweiback is not here yet. Lawrence is not here yet. And Wilson is not here yet. We still have 4 minutes, but I'll go ahead and do the normal announcements. I'm going to save some time for our lecture since I repeat myself anyway. So, as usual, and I'm not worried about anybody missing this because I say the same thing every day. Attendance is mandatory, as in I have to turn in your numbers when you were here, when you were not here to the university. It is also, participation is great. So remember, it's one whole letter grade of your whole, your entire semester. One letter grade is going to be attributed to your attendance, more specifically your participation. And I qualify that statement, I'm making a very specific there because like I mentioned about a week ago, even if you have an excused absence and you miss, you still like for your participation. Like, so if you have an excused absence, then when I report that to the university, you're okay, right? You didn't miss anything, it was an excused absence. But as far as grades are concerned, even if you're gone for a legitimate reason, you still need to watch the video or join us online if you need to. That's how you get your participation points. You, just by being here, automatically get your participation points. However, those are some points. So always be ready for me to call an audible. Always be ready for me to change it up. Because I always say we have the attendance words that I say throughout the lecture. One day I might come in and quietly be like, hey, today you have to send me the words. So make sure you're paying attention. Because I want to make sure you're paying attention, and that's why I might do that one day. Today's not that day, so don't worry about that. But anyway, again, on that note, if you're watching the video at a later date, as usual, every time I say an attendance word, you need to take a screenshot and write down the word, and at the end of it, you need to send me all the screenshots, all the attendance words. And the last attendance word is going to be you asking me a question about the material covered in this lecture. So, as you're going through the lecture, or as I'm going through the lecture, keep that in mind, that that's your last attendance phrase. And as always, so far, if you're here, you don't have to send those words in, but if you do send them in before 9 a.m., you will get extra credit for your participation grade today. So any questions about attendance and attendance grading? Smith walked in, so let me go ahead and mark them here. Oh yeah, speaking of which too, kind of jumping around a little bit. Just to remind you, since midterms are due next week, there's not much you can do about it right now, but anyway, if you've missed a class or a bunch, you can send me an email. I give you a list of the days you missed, and then you can go back and watch those videos. Send me that list of words and screenshots so you can get your credit for those days you missed. And again, as far as midterms are concerned, it's probably too late for that because I'm turning those grades in on Monday, basically. They're due on Tuesday. I'm hoping to get them in on Monday. So obviously, if you just get a bunch done over the weekend, that will help you, but not for the midterms. I'm not going to have time to grade all that. So for the midterms, it's too late, but we're only at midterms, so it'll still help you when it comes to your entire grade. Let's see. Friday, as always, my office hours on Fridays are 9 to 12. That kind of goes back to this last bullet point here again. When midterms due, if you need me, please let me help you. Also, I have to do October is when our self-reports are due for professors and instructors, right? So we have to do our evaluations in October, and part of our evaluations are based on the student evaluations that you do at the end of every semester. So I've been recently reading mine from last semester. So I can't emphasize this enough. It's so upsetting to me. If you need help, ask me. I hate when I'm getting all these, this was so difficult, this was so difficult. I had problems with this, I was confused with that. I get a lot of those, but then I get like 1 or 2 people every semester who actually actively ask me for help. So if you think something's hard, tell me it's hard. Don't wait until the end to complain about it. Tell me it's hard. Tell me you don't understand. Let me help you. Anyway, 8 o'clock, so we're good. We have less than 1 minute. So yeah, office hours today from 9 to 12. I'm in person. I'm also online, so if you need to meet me, let me know. I'm happy to help. I'm here to teach you, so I'd love to help you. Instead of just letting you do a pre-lab on your own, I'd like to walk you through it to make sure you understand it. Right? Instead of just that's your grade, I'm done grading it. I'd rather talk to you and explain why this is wrong and how you can fix it, because I want to teach you. Anyway, any questions about my office hours? All right, it is 8:01. Let me finish attendance one last time. We'll go through the list. Brumfeld is not here. Champion is not here. Gross is not here. Gunther is here. Randall Hill is not here. The other Hill is here. Jackson is here. Keys was the first here. Perez is not here. Sigmund is here. Slaughter is here. Smith is here. Stover is not here. Tompkins is not here. Van Nest is not here. Watson, not here. Young is here. Zweibeck is not here. Lawrence is not here. Wilson is not here. Did I miss anybody? Okay, nice and easy then. Okay, anyway. Just as a reminder, Lab 6 is past due. I was surprised. I went through, maybe I was missing emails, because every time you submit a lab, I get an email for it. And I was going through it yesterday and just noticed a lot of people just didn't even turn the photosynthesis lab in. I don't know why, but anyway, it's past due. I'll remind you, the official policy for late work is that officially, it's not accepted. I don't take it. Unofficially, go ahead and turn it in, and I promise my best that I'll try to get it great. Right? The only caveat is I always prioritize new work. Since I have 218 students this semester, I have a lot of new work to grade. So the sooner you turn it in, the better. And yeah, if you need help, let me know, right? Because now it's been a while since you did that lab. So if you're just looking at the data and be like, what the hell, how do I answer this question? I don't even remember what happened. That's what I'm here for. You don't need to be ashamed about that. Come and say, hey, it's been a while since we did that lab. I don't even remember what specifically happened here. Can you refresh my memory? And I'd be happy to help. So yeah, that's past due, photosynthesis. Lab 7 was technically due on Wednesday, the one that I said you didn't have to meet, but it's past due today. So if you need my help, again, let me know. I was here on Wednesday to help anybody who wanted it. No one wanted help. But I'm still here to help you. So when you're working on that today, you're like, I'm not quite sure I understand. Let me know and I'll help you. Yeah. Oh, and I got some good feedback. And I'll go ahead and address this. One person, some of the feedback said, could you get clearer pictures like for the karyotypes? And I wish I could, but I don't make those pictures. I have to find them on the internet. So speaking of which, for extra credit, if you find some other pictures of karyotypes that have what I need, like that 3 chromosomes for 18 or 3 chromosomes on the Y, whatever, if you can send them to me, I'll get you a little extra credit for that. But anyway, any questions about the labs and that are due today? Past due, all right? Again, the pre-lab for next week is due today. As I've already mentioned, there's 1 set of video questions. Make sure you take the screenshot and all that, insert it in there. There's 1 set of introductory questions. So after you read the introduction, answer those questions based on the introduction, because that's proof that you read the introduction. So don't look up the answers. Give me the answers that come from the introduction. And then, and this is where most people mess it up, so make sure you're aware of this. Well, not this part, everyone got this so far. There's 1 set of hypothesis questions. And then after that, you need to keep going, and there's 2 tables where you need to go ahead and fill a part of it out. And I highlighted these in green because all that stuff's highlighted in green. So as you're doing the lab, the pre-lab, just keep scrolling down and see the stuff highlighted in green. And again, if you need me, I'm here to help. So far, the people who have done the tables did it correctly, which is mind-blowing to me, because usually people mess it up, and I can see why that gets a little bit tricky. But obviously, if you mess it up, I'm here to help. So any questions about the pre-lab that's due today? All right, really quickly, the normal stuff. Exam 1, you can still retake it, but that closes on Sunday. So you can no longer retake the exam after Sunday. You have nothing to lose. Your grade will not go down. You could get a 0 on your retake for some reason. I don't know how you would, but if you did, it wouldn't affect your grade. So if I were you, I'd retake the exam while you still can. You retake it as many times as you want. Let me know when you're done so I can adjust your grade. Exam 2 is also due on Sunday. So, make sure you get the exam done. If you guys have friends in this class, please let them know. Because even though I've been saying this I've been doing it on repeat every day for the past 2 weeks, someone's still gonna be like, oh, I didn't know the exam 2 was due on Sunday. So let them know, please. And then finally, like I said earlier, midterm grades are due next week. And, I wouldn't worry about them. No one ever told me that when I was a student. There's nothing to stress about. It just lets you know where you're at, which you can tell anyway because you can get online and see your own grades. You could have an F at midterms and still in the class with an A. Take a lot of work, but it's possible. And it's like never on your permanent record. You know what I mean? Like when you're applying for a scholarship or a grad school, no one's ever looking at your midterm grades. So don't let it worry you too much. Any questions about announcements or reminders? Okay, in that case, the first word for attendance is anniversary. Tomorrow is my anniversary with my wife. Thank you. All right, let's jump into it. So we ended up talking about metaphase 1. So to remind you the big picture, the really big picture for exam 3, which is the one that's going to be due in about a month, that's covering basically cellular reproduction. That's the property of life that we're mostly covering for exam 3. The previous chapter we talked about mitosis, which is how we do asexual reproduction, right, where cells divide and make perfect copies of each other. In this chapter, we're talking about meiosis, which is sexual reproduction, right? This is talking about how we make sperm and egg, aka gametes. So we talked about meiosis in the big picture, which there's meiosis part 1 and meiosis part 2. Meiosis part 1 split, which is what we're in the middle of talking about, splits apart the homologous chromosomes, as opposed to meiosis 2, which we're going to talk about later, which is where we split apart the sister chromatids. And this is where we left off. So we were talking about metaphase 1 of meiosis, right? So the first metaphase of meiosis. This is the last slide we talked about. I just really want to point out again that this independent assortment is a very, very important concept. You're going to need to understand it later. Past this chapter, it's going to come back. Independent assortment is like saying, well, again, since we're talking about metaphase, if you remember, in metaphase, all those chromosomes line up together. And in metaphase 1 of meiosis, each of the homologous chromosomes are set in the middle. So like you got your mom's chromosome here and your dad's chromosome here. And then maybe your dad's chromosome here and your mom's chromosome here. And then maybe your dad's chromosome here and your mom's chromosome here, whatever. The point is, all 23 pairs line up in the middle of the cell, and it's not all mom on one side and all dad on the other. Well, it could be, but it's all random, right? There's no pattern. That's what independent assortment is. Independent assortment is. It's a very important concept. So anyway, any questions about that slide? All right, this slide doesn't belong there. It's out of order. Let's talk about anaphase 1 and telophase. So again, we're reaching the end of the first round of meiosis. And again, it's basically the same as mitosis, which is what you learned previously, except now, again, we haven't separated the sister chromatids like we do in mitosis. In this case, we've separated the homologous chromosomes. And this will make more sense. Let me just show you the next picture. There we go. So these homologous chromosomes have been pulled apart. Wait, I really did skip ahead. Anyway, this slide is not what we should be looking at, but this part's okay, right? So we have these homologous chromosomes, right? Like again, the one from the mom on one side, the one on the dad on the other, and they've been pulled apart. The homologous chromosomes are. This is what we just finished talking about, which is meiosis 1. Notice too, to remind you of stuff from when we talked about in the previous discussion, this mom chromosome's got little chunks of dad at the tips. And those that dad chromosome has little chunks of mom at the tip. That's because they did crossing over. And remember, that happens during prophase 1 of meiosis. So all important concepts, independent assortment and crossing over. That was meiosis 1. We're now done talking about meiosis 1. Now we can jump into meiosis 2. Are there any questions about meiosis 1 before we jump into meiosis 2? Back to the original the slide we were looking at previously. So, big picture before we start looking at all the little stages of meiosis 2. The big picture for meiosis 2 is that it is essentially the same as mitosis, except the end products are cells with half the genetic material, right? So, remember with mitosis, if you had a diploid cell and it went through mitosis, then you would have 2 more diploid cells, right? Or they would turn into 2 diploid cells because it's a perfect copy of the mitosis. In meiosis, we're cutting it in half. So we start with 1 diploid cell, end with 4 haploid cells. That would definitely be a test question. So with meiosis, you start with 1 diploid cell, you end up with 4 haploid cells. Another thing, oh no, it's right there. 4 genetically unique haploid cells. So that shouldn't be hard. And I don't intend for this to be hard, but on the multiple choice question, it is a little bit hard because if you're in a rush, you might see something like 4 haploid cells, and that might catch your eye and like, yep, that's correct. And it might only be partially correct because the more correct option in that multiple choice question would be 4 genetically unique haploid cells. So make sure you're paying attention to the chart, look for the best answer, not just the right one. Does that make sense? All right, so again, there might be an option that says, what's the results of meiosis 2? And again, one of them might say 4 genetically unique cells, but then which would be correct, but the other one might say 4 genetically unique haploid cells, which would be more correct. So pay attention to that part of the exam. Anyway, any questions about that? All right, one thing that's not written on here, because it's implied on this first main bullet point, it's essentially the same as mitosis, in that, just like in mitosis, now finally we're separating just like mitosis. In meiosis 2, not 1, we just finished talking about that. In meiosis 2, we are separating the sister chromatids, just like we are in mitosis, right? Meiosis 1, we separate the homologous chromosomes. Meiosis 2, we separate the sister chromatids. If there's no questions, we'll look at the picture that shows all of it together, all of meiosis 2 together. Prophase, pretty much as usual, right? The nuclear envelope has disappeared, which makes sense because you need to eventually you're going to move things to the other sides of the cell. So you need to get rid of the thing that's holding them together. This mitotic spindle is forming. If this was animated, you would see before we even get into metaphase, these mitotic spindles would attach to the chromosomes. And they do, and then they start moving towards the center of the cell, which is not, you can't see it because it's not animated, but that's what you would see if it was animated. And then once they actually get to the middle of the cell, that's when we consider it metaphase. right? So here you have their chromosomes lined up in the middle. You've got these spindles pulling it apart. It's like a tug of war that you cannot see because this is not animated, but it's tugging and it's pulling. And eventually those things will break apart. And once they're broken apart, we then consider that anaphase, right? And now they're moving. Again, it's not animated, but if it was, you could see those things slowly moving towards opposite ends of the cell. You would also see the cell changing shape and getting a little bit more long. And then once they finally got to the other sides of the cell, that's what we would consider telophase. Of course, meanwhile, while this is happening, the cell itself is pitching itself off, which is what we call cytokinesis. So as far as this picture is concerned, it might as well be the same as mitosis. The only thing different as far as the picture is concerned is because we're talking about meiosis, the artist had the foresight, they thought about making sure that these chromosomes still have those little multicolored chunks on there to indicate the crossing over had occurred. Because when we talk about mitosis, that's not a discussion, right? But in meiosis, when we do talk about crossing over. So that's it for meiosis 2. Are there any questions about meiosis 1 or meiosis 2 before we move into the next phase, which is going to be a big review that's going to compare mitosis and meiosis, because it's important that you understand the difference between the two. All right. The next word for attendance will be FSU, since that's where I met my wife. So FSU is the next word for attendance. Anyway, next, again, like I said, we're going to review. And there's going to be quite a few questions where you need to know the difference between meiosis and mitosis. So here we go. For both meiosis and mitosis, there's only one duplication, right? So when we're talking about the cell cycle, we only go through that S phase of interphase once, right? Your cells are only duplicating, or your chromosomes are only duplicating once. But the number of times they divide, that's what makes them different, amongst other things. Because in mitosis, as you know, it only divides once, right? So it duplicates, so it doubles everything, and then cuts it in half. So basic math will tell you that brings you back to the original number, right? Whatever you have, if you double it and then cut it in half, you're back to your original number. Meiosis, on the other hand, you double it, then you cut it in half, then you cut it in half again. So you're left with half of your original number with meiosis. Now, of course, with humans, that means, we're going to end up with 4 cells that have 23 chromosomes. Not 23 pairs, but 23. But of course, it doesn't matter what the species is. Whatever number you start with, it's going to double, then cut in half, and cut in half again. So if you had a species that had 10 chromosomes, normally, right, then it goes through S phase of interphase. Now it has 20. Then it goes through the first round of meiosis, so it's back down to 10. Then it goes through another round of meiosis, and now it's down to 5. So any questions about this slide? There's going to be more comparing and contrasting of meiosis versus mitosis, but the first one, this is it for the first one. We'll talk about cell division. Well, cell duplication and cell division. So any questions about that? Okay. The events that are unique to meiosis only happen in meiosis 1. So there's different ways I can word that, right? So I can say which one is more like mitosis? Meiosis 1 or meiosis 2? And the answer would be meiosis 2, right? Meiosis 2 is more like mitosis. Or I could say more like the bullet point says. Which one has unique events unique only to meiosis? Meiosis 1 or meiosis 2? Oh, that's meiosis 1. So think about all the different ways I could ask a question for that first bullet point. That will be a bullet point. So again, meiosis 1, that's where all the unique things to meiosis happen. Meiosis 2 is virtually identical to mitosis, right? Because that's where we're separating the sister chromatids. Meiosis 1, again, that's when we're separating the homologous chromosomes. Meiosis 2 is when we separate the sister chromatids. And again, unlike mitosis, meiosis 2, or the whole process of meiosis, really, when you think about it, it yields haploid daughter cells, right? So not diploid. We start with diploid, we end with haploid. We start with 1 cell, we end with 4 cells. We start with 1 cell, we end with 4 genetically unique haploid cells in meiosis 2, or meiosis. In mitosis, we start with 1 diploid cell, we end with 2 diploid cells, genetically unique diploid cells. So those are big differences. And here's a picture of everything we're saying, right? There's everything we're saying. You can see these are basically the same cells, and one's going through mitosis, one's going through meiosis. This one that goes through mitosis ends up with two perfect copies of itself. This one that's going through meiosis now has 4 new cells, and they're all genetically unique from each other and unique from the parent cell. This one starts with a given amount of genetic information. These two have the same amount of genetic information. This one starts with a given amount of genetic information. Each one of those has half the amount of genetic information. Hopefully that part's at least really easy to remember. Because you know what sperm and egg are, you know how that works, you know how sex works. You know that sperm and an egg come together, and that's where the human's going to come from. So logically, it makes sense that your sperm and your egg must have half of the genetic information. Otherwise, you would have, when those cells came together, you would have double the genetic information for most animal species. That would be a bad thing. Now, it's not always a bad thing for other species, if you want to look into that, but for extra credit. Any questions about that? So that is the end of the review comparing meiosis and mitosis. Next, we're going to move into talking more about this idea of crossing over and independent assortment. So we're done talking about that. Are there any questions about this comparing and contrasting between mitosis and meiosis? Okay, so again, we've already talked about this. Now we're circling around. We're going to talk about it again because it's so important. Because to understand things you're going to learn later in the semester, you really need to understand these origins of genetic variation. So let's talk about it. As I've already mentioned, I'm just saying it again, and you're seeing it in writing again, so hopefully you'll get this question on the exam. The offspring of sexual reproduction are genetically different from the parents of one another. Mind-blowing, right? Did you know that you are not a perfect clone of your mom, and you're not a perfect clone of your dad, right? You're genetically unique. Even there are some people where they're like, you can really tell that they're related, that, oh, they've got to be father and son or mother and daughter. Sometimes it's really obvious. They seem almost like they're almost perfect clones, but they're not, right? They are genetically unique. Also, even though it's not on here, unless they're twins, they're also genetically unique from their siblings, right? Common sense, you all know this. And again, even when siblings look very similar, unless they're identical twins, they are genetically unique from each other. So how does this happen? How does meiosis produce genetic variation? Let's talk about it. The first part is independent assortment. And we've already talked about it. Now we're really going to focus on it and go into some more detail. So again, in metaphase 1, that all these homologous chromosomes lined up together, right? And I'm drawing them as an X because remember each one, right? Let's say that one's from your mom, that one's from your dad, but each one, they haven't been separated yet because it's meiosis 1. So even the sister chromatids are still together, which is why they're looking like X's. Anyway, they all line up in the middle, right? And again, what's not happening is it's not like all the mom chromosomes line up on one side and the dad chromosomes line up on the other. That's not what's happening. It happens independent, right? So it could be mom, dad, dad, mom, dad, right? Think about that 23 times, right? That's what's happening. So here's a number that you need to know. And these are the astronomical numbers I was talking about on Wednesday. For humans, they have 23 pairs of chromosomes. You can do the math. You're not going to have to do the math because I'm giving it to you. So that would be 2 to the 23rd. That means there are 8 million possible combinations of how your mom chromosomes and your dad chromosomes can line up. Meaning, statistically, if you were to look at 8 million of your sperm, or if your eggs, if you had the time to do that, and look at all of how their chromosomes are lined up, each one of them would have a different version of how the mom and dad chromosomes are lined up in the middle. 8 million. So that means, another way of saying that is, and this is only based on how they're lined up, if your parents had 8 million children, the chances are that each one of you would be genetically unique. 8 million children. Think about that. That's an incredible number. 8 million, right? And then, and that's only, sorry, I'm underselling this. That's only talking about how the sperm is created, or the egg. So then the chances of that particular sperm coming together with that particular egg would be 1 in 64 trillion. So that's more accurate, sorry. If your parents had 64 trillion kids, it would be statistically acceptable to think that you would still be genetically unique from your siblings. All based on how your mom and dad chromosomes lined up when you produce the sperm and the egg. 64 trillion. That's an incredible number. And that doesn't even take account for crossing over, which we'll talk about in more detail in the next slide. So yes, even though there's 64 trillion possibilities for the way your mom's egg and your dad's sperm could have come together, then add on to the fact that even if some miracle happened and you had two that had the same exact lining up of the chromosomes, like independent assortment, then you have to take into consideration some of them have had crossing over. So even though it may be the same combination of mom, dad, mom, whatever, they're still not going to be genetically unique because some of them have crossed over, some of them haven't, some of them have crossed over a lot, some of them have crossed over a little bit. So basically what I'm saying is it's damn near impossible for you to get anybody but you, which is a very interesting idea. And I mention this every semester. It's a little bit risque, and now I know that I've got like high schoolers watching this too, so I'm trying to figure out how to say this properly without getting too vulgar. But think about, well, you being you, right? When your mom and your dad had sex to make you, it had to happen exactly that way. Otherwise, it would have been a different sperm, and it would not have been you. Because every sperm, I've demonstrated that every sperm is going to be unique, right? So if your dad didn't finish exactly when he finished, and if they weren't in the exact same position that they were in, it would have been a different sperm, and it would not have been you. To me, that's just mind blowing. The idea, like, your dad could have, or mom, whoever, maybe one of your parents got a little bit pissed off earlier in the day. So then they weren't in the mood right away, and it took them a little bit longer to get in the mood. And because of that, it's you now instead of some other version of you, right? I don't know. I think that's mind blowing. It's like Back to the Future type of stuff. The butterfly effect. You just change one little thing, and you're going to have a whole different person. But anyway, more important, back to academics in the exam. Here's the number you need to know, right? There's 8 million possible combinations for humans of how the sperm or egg will be created. Strictly on the conversation of how the mom and dad chromosomes line up. Here's a picture of what I'm saying. Of course, this species only has 2 chromosomes, right? We have 23. So this is a lot easier to visualize. So in this possibility, there's a mom on one side, dad on the other for both. On this one, chromosome 1, you got mom on one side, dad on the other, dad on one side, mom on the other. So again, imagine that 23 times, all the different combinations. 8 million different combinations. Anyway, so this thing goes through meiosis 1, the homologous chromosomes separate, and the sister chromatids separate. And what you're left with here, these are your 4 different possibilities. In this case, since it's such a simple species that only has 2 chromosomes, in this case, you do have 2 identical gametes, right? Those 2 are the same as each other. These 2 are the same as each other. In this case, when they've lined up differently in the beginning, they separate differently. So now you have, this has mom and dad. This one has mom and dad too. But anyway, the point is that's where one of the places genetic variation comes from. It's a very important concept. This is why sexual reproduction is such an interesting thing, such an impactful thing. So that's it for independent assortment for now. Later, there'll be another chapter where we talk about independent assortment again. And maybe even another chapter after that. So make sure you understand that. Is there any questions about that? All right. And once again, crossing over. We've already talked about it before. Let's talk about it again. The next word for attendance will be Charleston. That's where my wife and I got married. When we first bought our first house, Charleston. So anyway, crossing over. Like we've already mentioned before, this is the exchange of corresponding segments between homologous chromosomes. It's a fancy way of saying when those homologous chromosomes come together, they'll just swap chunks, right? And this will make a lot more sense when I show you this picture on the next slide. Again, this occurs during prophase 1. That might be a test question. You definitely need to know that it happens during the first meiosis. I don't know if I'm going to get so specific to ask you which part of that first meiosis, but yes, prophase 1 is when it happens. And it results in gametes that have chromosomes that are partially from the mother and partially from the father. So again, when we were talking about crossing over, we were just saying, all right, that's a mom chromosome, that's a dad chromosome, that's a dad chromosome, that's a mom chromosome, that's a dad, whatever. Now we're saying, yeah, there's that, but also that dad chromosome It's got a little bit of mom in it. And now that mom chromosome's got a little dad in it. Here's what we're talking about. It might be a little bit hard for you to see, but yeah, you can see here in prophase 1, they're close to each other, so they literally mingle and swap chunks. So now you have a mom chromosome with dad chunks, and a dad chromosome with mom chunks. And like I said when I first mentioned this, it doesn't always happen like this. This particular time, it happened on both tips. Sometimes it only happens on one tip. Sometimes it doesn't happen at all. Sometimes it's a huge chunk. Sometimes it's a small chunk, right? So this is very, very random. So again, even forgetting about the 64 trillion possibilities of that one sperm coming together with that one egg, then you like the numbers are even bigger than that, because even with those 64 trillion possibilities, now you add this into it. So it's just incredible. The numbers are incredible. But that's crossing over. Are there any questions about that? All right. It's pretty easy then. I might be able to finish this chapter up. Nice. Let's talk about what happens when things go wrong, right? Let's talk about what happens when meiosis goes awry. This is slightly important too. I wish we could have done this before you did the lab, because this is the second part of the lab. Remember, we have already talked about karyotype, so that's good. You guys know what a karyotype is. It's when you can actually see the chromosomes. So in the lab, you can see that there's problems with those chromosomes, but now we're going to talk about how those problems come to be. So what happens when there are errors in meiosis? This is what we're going to talk about. It can result in genetic abnormalities that range from mild to severe to fatal. And in the lab, that's what you were looking at, right? So you looked up, you looked at the karyotype and like, oh yeah, that one's got 3 number 13 chromosomes. So I'm going to look this up and be like, all right, what's that called? Oh, this is what it's called. And here's the prognosis, right? Here's what's wrong with somebody who has that many chromosomes. So let's talk about it. This occurs because of something called non-disjunction, and I'll probably ask you about non-disjunction on the exam. It is when chromosomes fail to separate. And it's an easy word to remember. It's kind of in the name, right? Non-disjunction. It just sounds like what it is. They don't separate. Of course, as I'm going to mention later, I think you're going to see it on the, right here. So they're failing to separate. Now, it could be the homologous chromosomes that didn't separate, if it's in meiosis 1. Or it could be the sister chromatids that didn't separate, if it's in meiosis 2. And obviously, as you can imagine, that's going to change the outcome. And we'll talk about that change in outcome. But yeah, for now, the biggest thing you need to know is what non-disjunction is. And that is when the chromosomes don't separate. And the rest of that just makes sense, right? If you notice the chromosomes don't separate, obviously the second bullet point just makes sense. If the chromosomes don't separate, they're going to produce gametes that don't have a normal number of chromosomes. Right? So your sperm or your egg will either have too many chromosomes or not enough chromosomes. And this will make probably more sense when I show you the next slide that has a picture. Well, not the next slide, but it's coming. Any questions about this slide? Okay. There's some more words you need to know. When you have the correct number of chromosomes, that is called euploid. EU, that prefix generally means true. It's a prefix that means true. Like, so you have the true number of chromosomes. So I would assume, and I don't know this, you can never tell, especially when it comes to sex chromosomes, and you can't judge a book by its cover, but I would assume everybody in here has a normal number of chromosomes, but you never know. But when there's an error in the chromosome numbers, we call that aneuploid. So euploid is the right number, aneuploid is the wrong number, right? The non-true number of chromosomes. And even that can be subdivided into 2 categories. Aneuploid includes monosomy, however you want to say it. That's when you've lost a chromosome. And then trisomy, where you have 1 extra chromosome. And this is just for humans. It actually gets a little bit more complicated than this if you want to look into it for extra credit. It does get more complicated. Like again, for example, plants, if you can quadruple, so if you can give them 4 times the number of chromosomes, sometimes it can be beneficial for plants, not for humans. Also, then there's things like fungus, if you want to look into that. When we talk about mammals, sex is pretty straightforward. Well, compared to fungi, it's pretty straightforward, right? You either have male, female, or some other versions. We've had other issues that we've talked about previously. But for fungus, sometimes there can be there's not even male and female. There's just literally hundreds of sexes for one species, but not important for this course. You can look it up for extra credit. All right, finally, here's the picture I was talking about that kind of shows everything. This picture's from the old textbook. So if you're looking at your textbook and you're looking at this, and you think this one's easier to study, then you can download this PowerPoint from the WVSU online. But here we go. Here we have non-disjunction in the first round of meiosis, right? So because of that, the homologous chromosomes failed to separate, right? So now those things are going to go their way. Now these two new cells are both messed up, and then they're going to go through another round of meiosis. Now none of these are normal, right? So this one has too many chromosomes, one too many chromosomes. This one has one too many chromosomes. This one's missing a chromosome. This one's missing a chromosome. All because of that one non-disjunction in the first round of meiosis. Here, in the second, or this version, the non-disjunction happens in the second round of meiosis. So it's not the homologous chromosomes that failed to separate. They did that just fine. It's the sister chromatids that failed to separate. And the good news with that is, at least we still have this one. This one, that one separated just fine, so we have two viable gametes, right? Two egg or sperm that work. Here, this one's messed up, right? This one has one too many chromosomes. This one has not enough. So in a sense, if I were to ask you a question, say, which one is potentially worse, non-disjunction of meiosis 1 or non-disjunction of meiosis 2? The answer would be meiosis 1 is worse, right? Because when it happens, when the homologous chromosomes fail to separate in that first round, then they're all going to be messed up. Here, at least half of your sperm or egg are going to be okay. It's the other half that aren't. Any questions so far? All right. So the next slide I'm going to show you, which is another visualization, again from the old textbook, it's going to show an abnormal gamete, so an egg or a sperm, fertilizing a normal gamete. In this particular example that I'm about to show you, it's going to result in a zygote. Remember, a zygote is what happens when you bring, after fertilization, right? Bring the gametes together and you create a zygote. It's going to result in a zygote with 2n plus 1 chromosomes, meaning it has the normal set of chromosomes, but it has one extra chromosome. And because mitosis works the way it does, remember, meiosis only produces the sperm and the egg. After those sperm and the egg come together, then mitosis takes over and it starts making a perfect copy of that cell, right? You get one cell turned into 2 cells, turned into 4 cells, 8 cells, 16 cells, so on and so forth. But mitosis makes a perfect copy. So if you give it a cell that has the wrong number of chromosomes, or zygote, in this case, that particular type of cell, then it's going to copy it just as it was given it. So then all the cells after that are going to have that abnormal number of chromosomes. So if the organism survives, which it doesn't always, it will have an abnormal karyotype and a syndrome of disorders caused by the abnormal number of genes, which again goes back to what I was saying. That's basically what the second half, the last portion of your lab is that's past due today. So the one that we did on Wednesday, that's half of the lab. Here's a picture of what I'm talking about. Here's a normal sperm cell, right? This one's got 2 different chromosomes, right? This is chromosome 1 and chromosome 2. This one is abnormal. It has chromosome 1 and chromosome 2, except this one has an extra chromosome 1. So when those things get together, what we should have is 2 chromosome number 1s, and there we go, 2 chromosome number 1s and 2 chromosome number 2s. That's what we should have, but now we also have this additional 3rd chromosome number 1. Of course, the numbers don't matter. And you can see no one ever said that's chromosome number 1, that's chromosome number 2. I just gave them that number. Just because, at least with humans, we number them 1 through 23, and we do it by size. So number 1 is our largest, number 2 is our second largest, so on and so forth. Anyway, any questions about this slide, this picture that's not from your textbook? All right. So we're going to talk about, there's all kinds of different disorders. We're only going to talk about one of them. Well, that's not true. We're only going to talk about a handful of them. The first one we're going to talk about is Down syndrome. I'm sure mostly because you guys have probably already heard of it. There's going to be few, if any, questions about this on the exam. Because as far as this semester is concerned, this information I'm giving you is not very important. Because if I teach it to you and then you brain dump it, you'll be okay in the next chapter or the chapter after that. Unlike independent assortment crossing over. That stuff you need to keep to understand what I'm going to teach you later. This, I mean, this will be relevant to your everyday life, maybe, but not very relevant to this semester. So anyway, let's talk about it. Down syndrome is caused by something called trisomy 21. Hopefully you know what that means, even if I didn't teach you. or even if you hadn't heard of it before, hopefully it's in the name. Trisomy 21. Oh yeah, that means there's 3 number 21 chromosomes, right? So instead of having 2, instead of having a pair, there's an extra. That's trisomy 21. It results in 47 total chromosomes instead of 46, right? Because remember, a normal human, a genetically normal human has 46 chromosomes. So in this case, they would have 47 instead. A person that has trisomy 21 is said to have had Down syndrome. It affects about 1 in 850 children. It is the most common chromosome abnormality in the U.S. and the most common serious birth defect in the U.S. And the risk increases with the age of the mother. And if you want to look this up for extra credit, feel free. I always found that interesting. Like, what is it about the mom's age that causes this? There's an answer. Let's see if you can find out. But it's good. It's a little bit deeper than what I've taught you, so I won't even hint at the answer yet. But why is it that? Why is that? Like, why is it that when the mom's age increases the risk, but not dad's age? You look at people like Mick Jagger. I think he had a kid in his 80s, right? That sperm, that old crusty sperm, still made a genetically normal human. But look into it if you want. Anyway, specifically, when we say increases with age, 35 years and older, that makes a mother a candidate for prenatal screening. So they're like, yeah, we definitely want to get a hold of this and look ahead. Anyway, again, as far as the exam is concerned, that's not very important. Neither is this. A person with Down syndrome has characteristic facial features. They're also very often have shorter lifespans. I put a little star next to that to remind myself of something. Let me see what that is. Yeah, usually not always. They don't always have a shorter lifespan, but usually that is the case. They have varying degrees of developmental delays. That's another thing. These 2 bullet points are things you could look into as well. Like, what is it? How come there's varying degrees of lifespan? Why is there varying degrees of developmental delays? We're talking about somebody who has 1 extra chromosome, an extra chromosome 21 for that matter. And remember, for humans, or for every species, any given species, all the chromosomes are the same. So whatever genes that person has on their chromosome 21, I have the same genes. You have the same genes. Every human on Earth, ever, who's not had some sort of genetic abnormality, has the same genes on their chromosome 21. So how is it that one person who has an extra 21 will live longer than another person who has an extra chromosome 21? Why do they have varying degrees of developmental delays? Anyway, any questions about this? All right, here's a karyotype that shows it. Where is it? 21, 21, 21, 21. There it is. Wait, that's a normal karyotype, right? That one has a pair of chromosomes on 21. This one has an extra pair of chromosomes on 21. Also, to the person who gave that great feedback, is like, hey, can you get better karyotype pictures? And yes, I would like to. I like these better. I know it's a little bit hard to see. If you could see this screen, these look a lot better. But the problem is I want to keep it consistent, and I couldn't find a bunch of these that had more than trisomy 21, right? So I wanted trisomy 21, I wanted extra chromosome 18, extra chromosome 13, I wanted a sex chromosome abnormality, and I wanted to make sure that all the karyotypes looked similar other than that, and that was my challenge, just so you guys know. If you go digging for that extra credit, find me some extra karyotypes. That's another thing that I failed to mention. I want all the karyotypes to look the same other than the number of chromosomes, because that's the challenge, right? It's just to look closer, like, that's how that one's different. So again, I don't want like one in color and then one in black and white. I prefer them to be all identical, other than the number of chromosomes. Anyway, any questions about that? Okay, we're getting there. I might be able to finish this chapter today. I know you can't read that, but now let's talk about abnormal numbers of sex chromosomes. So this is basically an extension of the conversation we just had. The whole conversation we just had was about non-disjunction and about how you can have extra chromosomes. And actually, before I even get into that, let's talk about something else for extra credit if you want to write about it. We've talked about having an extra chromosome 21. We're about to talk about having extra sex chromosomes. But now go in there if you want, look at other stuff. What about extra other chromosomes, like some of the which that you saw in lab? Chromosome 18, chromosome 13. What about the other ones? You never hear about an extra chromosome number 1. Why is that? And I actually don't even know the answer to that. I think I do. I have a hypothesis. It's probably already been answered. But think about it. These are all size. Like chromosome number 1 is the largest, right? That's chromosome number 1. Here's little bitty chromosome number 21. So to me, it makes sense where you can have an extra chromosome number 21, and it's not going to make that much of a difference. Chromosome number 1 is huge, which means it has a lot of genes on it. So if you duplicate that thing, that means you're making a big difference in your genome. That's my hypothesis. I don't know this. I hope I was never taught it, because if I was taught it, that means I forgot it, which is even worse. But anyway, look into that for extra credit if you want. Let's talk about abnormal chromosomes, sex chromosomes. So again, non-disjunction, that can prevent any chromosomes from separating, right? Including these sex chromosomes. And remember, the sex chromosomes are the X chromosomes or the Y chromosomes. Generally speaking, a female human has 2 X chromosomes. Generally speaking, a female male has an X and a Y chromosome. But non-disjunction can upset this genetic balance, right? But it's a little bit less severe than with other chromosomes, like trisomy 21, like we just got finished talking about. You can look that up for extra credit if you want. Why is it that it's less severe? Part of it, as I just previously mentioned, I think has to do with the size, right? It's a lot smaller. These chromosomes are much smaller, which means they also have fewer genes on them. Anyway, here's the chart. You do not need to memorize this. You do not need to study. There'll be no point in the exam when I ask you something like, all right, what do you call the syndrome when a male has an extra Y chromosome? And what was the origin of the disjunction? And how many people in the population have it, right? I'm not going to ask you any of this. But you can look into any of this for extra credit if you want and write a paper about it. Especially this one's interesting. Are any of you criminal justice majors? No? Okay. Anyway, XYY is interesting. I've heard this, and I haven't confirmed it, or if I did, I forgot that I confirmed it. Anyway, you can see here XYY, that's a male that has an extra Y chromosome. You can see about 2,000 people in the population have it. However, XYY, Y is the chromosome that makes you a male, provides testosterone and stuff like that. So people who have that, I've heard the term, and it's not on here, super males, and they're extra aggressive because they have that extra testosterone. So I've also heard, and I haven't confirmed, and you can look this up for extra credit if you want. I've also heard that the numbers, if you like the prison population, it's not 1 in 2,000. It's a lot more common in the prison population, suggesting possibly that because these people have this extra Y chromosome, they're extra aggressive, and that leads them possibly to participate in violent crimes and things like that. Which is not to say, I'll be very clear here, which is not to say that if someone has XYY that they're more likely to be a criminal. Right? I don't want to do that. I was kind of saying the opposite. We're saying that if they're already criminals, a group of criminals together, the probability of them being XYY is higher. I hope you guys understand the difference. I'm not saying we should judge people by their karyotype, but oh my God, this baby's got XYY. Put him in a special school and I don't know, make sure he's already on probation before he graduates high school. I don't know. So we're not making those kind of assumptions. Any questions about that slide? As far as the exam is concerned, it's a very important slide. Okay, another thing we haven't talked about, so there's just not this idea of too many chromosomes or not enough chromosomes. Sometimes there's also damaged chromosomes. So there could be partial duplications and partial deletions. Right? So maybe with the crossing over, something went wrong. Or maybe when they separated, they mostly separated, but something got left behind, right? This is usually survivable, but obviously when there's something wrong with your chromosomes, it's going to lead to something, usually a physical or mental abnormality. Those are partial deletions and duplications and deletions. Then we have something called inversions. This is when the chromosomes detach and do a 180-degree rotation and then reinsert that part of the chromosome. And that'll make a lot more sense when I show you the next slide. This is usually less important or less detrimental because you still have the same chromosome information, right? The same genes are there. You just kind of change the order. And so that'll matter a little bit, but not too much. And then we have something called translocations. Translocations, I wish we had more time to talk about. They're really important as far as natural selection is concerned, but we'll probably never even talk about it again after this slide. But translocations are when a part of the chromosome disassociates and reattaches to a different chromosome. So that'd be like, remember crossing over, you have this mom chromosome, dad chromosome. They're homologous chromosomes. They're the same one. They swap chunks. This is like saying you have a chunk of chromosome 1, and chromosome 1, and it breaks off and goes down here to the end of chromosome 4, right? So that's a little bit bigger of a deal. Not as big of a deal as this first bullet point, because you still have the genes, they're just in a different place. Here's pictures of what I'm talking about. Here's an inversion, right? This is how it should be. It's kind of hard to see with this lighting. And all that's happened is this has come out, flipped itself around, and inserted itself back in. Right? So it's the same genes, it's just there in a different order. Here's a reciprocal translocation, meaning they've swapped, right? So this is, I'm just gonna make numbers up. Let's say this is chromosome number 1, this is chromosome number 20. I just made those numbers up, doesn't matter. But the point is, they're different chromosomes. So these things swap. So now you have a chromosome number 1 with a chunk of chromosome number 17 on it, and a chromosome number 17 with a big old chunk of chromosome number 1 on it. So again, in a sense, these translocations are basically, it's a lot like crossing over. But crossing over is okay because those are homologous chromosomes. These are not homologous chromosomes. These are different chromosomes, so you don't want them switching over. Next word for attendance will be Antigua. That's where we went on our honeymoon, Antigua. Anyway, let's wrap this up. Let's see if I can do it in a minute. This is also not from your textbook. This is from the old textbook. I love the old textbook because at the end of every chapter, they brought it back to evolution. And I left that out on most of the slides, but I left it in on this one. Many species reproduce sexually and asexually. So the question is, then what is the advantage of being what is the evolutionary advantage of asexual reproduction? What is the evolutionary advantage of sexual reproduction? Well, an asexual reproduction is advantageous. If you are an organism living in an environment, you're just supremely fit, right? You've adapted, and this is exactly the kind of environment that you thrive in, and the environment's not changing much. You don't need to change things up, right? You are great. So you can just make a perfect copy of yourself. On the other hand, if the things are changing, as they usually are, then it helps to have offspring. They shuffle things up and have all these genetically different offspring, because then as things change in the environment, one of those offspring is going to be more likely to survive and pass along those genes. And that is the end of it. You guys have a good weekend. I'll be online in the office for office hours until noon. I'm here to help you. Let me know. And don't forget, the last word for attendance is technically you asking me a question about the information presented in this discussion.